In today's video, we're going to continue to build on our energy model and how we can use energy to sort of analyze different situations. So far, just to recap sort of what we've done, we started with sort of a definition of work and building, off of F equals ma, Newton's first law. We did a bit of calculus, and this led to our definition of work, which was an integral from an initial position to a final position of that force dotted with some change in position, was equal to change in kinetic energy, right? And this was sort of our work kinetic energy theorem, where work on a particle caused a change in kinetic energy, where we defined that work to be um, this integral that we just talked about. ds. We went on with this and said, well, if we're looking at a constant force, F, it can come out of the integral. And for constant forces, we had just that the work was equal to the force dotted with whatever that displacement was. Um, Sorry, I switched from R to S here. And we talked about how to take dot products and do all of that. And we had also defined our kinetic energy is defined as 1/2 the mass of the object times the speed squared. So we looked at that, and that was all well and good. Then we built on this and said, well, what about friction and things like that, and discussed how when you have a dissipative force like friction or drag or something like that, it actually converts this kinetic energy, this macroscopic kinetic energy of the object, into microscopic energy in the system. We call that energy thermal energy. And when you're looking at a system or some situation where there is friction, we can calculate the increase in thermal energy as essentially the force of friction times the displacement, how far it's moved. Uh, and this sort of hand wavy can be thought of as this is the work done by that dissipative force, and it's taking kinetic energy away and converting it into this thermal energy. So we've done sort of all of these things, and we're starting to build this energy model where we can define our system, look at the kinetic energy, what external forces do work on it, and figure out how things go. Today, we're going to build on this with the concept of potential energy and go from there. So to introduce potential energy, one of the things I want to think of just a very simple example. Let's imagine we have sort of an empty universe. We just have two particles, particle A and B, and there's nothing else near them. So the only force we can think about is the force of A acting on B or B acting on A. They have an action-reaction pair of forces between them. Now, what would happen with this situation, right? Let's say they're just pushing each other away for whatever reason, right? Well, there's a few ways we can analyze this using energy. We can, and the first one is let's analyze them as individual systems, right? So in the first case, if we look at system A, just particle A as one system, well, it has some force, the one from B, acting on A. So it has force B acting on A, and there's nothing else holding it there. It's going to move. So there's going to be some work force times delta x, and it's going to have some increase in kinetic energy, right? If we look at the system and it gets pushed that way, it's going to accelerate that way and increase its kinetic energy. Um, so this is the work done on object A, right? I can do the same thing for the work done on object B. It's just going to be the force of A on B times its displacement, and that's going to cause its change in kinetic energy. I'll subscript these with B's, subscript this with an A, just to be consistent. But again, this particle is going to speed up going that way because it's got this force. It's going to increase its kinetic energy. So if we were trying to think of, all right, what's the change in kinetic energy of this particle A and B, it would just be, well, where A is the increase in kinetic energy of A, plus the work of particle B, which is just its increase in kinetic energy. And this whole, if we look at both particles together using this analysis, we would see that it's kinetic energy would totally increase. Now, if we look at both the system another way and look at particle A and B as one single large system, and they're interacting together, there are now no external forces on this system, right? This interaction between A and B is an internal force in that system. So the work done on that system is now going to be zero, right? There's no external forces that can be doing work on that system and adding energy to that system or taking energy away. So if I were to try and think of what's the change in kinetic energy of this system, I would get zero, which is very different than had I analyzed it this way. So the question has to come up, well, what are we doing wrong here? What's the discrepancy between the two? And it turns out the answer is potential energy. This interaction inside our system stores energy. There is an energy associated with that interaction, and we call that interaction the potential energy. And we're going to use the variable U to describe that potential energy. And to sort of reconcile these two, what we have is the change in potential energy is equal to negative the work done by the internal work done in that system. Or in this case, it would be negative the work done by A plus the work done by B. And we can sort of define a potential energy in our system associated with this interaction in this way. And what that means is now if we want to track the energy of this system, we have to worry about more than the kinetic energy. We also have to worry about that change in potential energy. So the work done from external forces causes a change in energy of our system, but that's going to be the change in kinetic energy plus the change in potential energy. And for this case, if there's no external forces, that's going to be zero work done. We're going to have our change in kinetic energy of the system. And given this sort of definition we've sort of shown here, this is going to be minus work A minus the work done on B, which if we rewrote it, this leads to work A plus work B is equal to the change in kinetic energy, which is the same thing we got when we analyzed it as individual atoms or individual particles. So there's a big benefit to doing this. Essentially, pun not intended, but it's a little less work sometimes to analyze the system as a whole and just consider potential energy. And there's a lot of mathematical reasons why we want to do this. But the gist is, when you have a system, if you include multiple elements to that system or multiple parts, those interactions between those internal parts of your system can have potential energies associated with them. And we need to keep track of those potential energies if we're considering the energies in that system. Right. So one very common and one we're going to see a lot in this course type of potential energy is gravitational potential energy. So let's say we're on Earth, pretty safe bet, and we have some object above Earth, right? Now, we can sit here and we could look at just this individual particle by itself and consider the force due to gravity on it and the work done by it. But one of the things that will make our lives a lot easier, rather than considering all the work from various forces on here, is to consider that potential energy of the Earth. So what we need to do is define our system as the Earth, as including the Earth in our particle, right? So we have the force of gravity on our object pulling down. We also have this force of gravity on Earth pulling it up. Remember, there's that action-reaction pair. But if we wanted to look at the change in potential energy of this system, it's going to be negative the work done on our object plus the work done on Earth, right? And if we look at the work done on Earth, well, it's going to be equal to the force of gravity is going to be constant in this, so it's just going to be the force of gravity on Earth dotted with the change in position of Earth, right? And it's safe to say that the Earth is so massive that for anything going on here, that Earth isn't going to be moving much. So the Earth doesn't really change its position. So the work done on Earth is zero. Um, we can also look at the work done on the object, and it's going to be the same sort of thing, force of gravity acting on the object, dotted with its change in position. I'll use y in this case because it's, assume it's going up and down. If I do this displacement or this work done here, this is just going to be the mass times the gravity times the y final minus y initial. Or if I expand that out, mg y final minus mg y initial. And that's the work done on the object. So if I want the change in potential energy due to this gravitational force, which is inside my system, that interaction between Earth and the object, I get 0 plus this. I get mg, the position of the object final, minus mg times the position of the object initial. Or what I can do is I can just define my gravitational potential energy as the mass of the object times that gravitational constant times the vertical position of that object. And we get this gravitational potential energy. And one of the really nice things about having this definition now is we no longer have to consider the sort of path this object took or how it moved or anything. All we have to do is consider the endpoints of that object, right? So if I have some object, that goes here and then it comes back down and follows some path to here, right? So this is its initial position, this is its final position, and I want to know the change in potential energy of that. It's just going to be mgy final minus mgy initial. And that doesn't matter, doesn't depend at all on the path it took. It's path independent. Um, so you can kind of save a lot of if you were to figure out the work done by gravity, if you were to just looked at this particle by itself and looked at the work done by gravity, you would have had to figure out the whole distance it traveled, the dot product between the force and the change in position, and all that math can get really, really complicated really, really quick. But since we have defined a potential energy, we don't have to do any of that. We can just focus on the endpoints. And our lives get much, much simpler. Hopefully, this will become clear in some examples, and as we get more comfortable with this. Essentially, again, I've been saying this sort of for a while now. All the energy picture is essentially bookkeeping where our energies are, and now we have to consider kinetic energy, potential energy, in particular this gravitational potential energy we've thought about, work done by external forces, and the changes in thermal energy, if there are any. And if we can keep track of these, we're kind of set for our system, for how to analyze these systems. So let's look at a quick example. And also, I'm going to use this example to highlight what can sometimes be a sort of confusing point for a lot of students, where the zero of potential energy is. So the example is simple enough. I have a 1 kilogram rock and it's 1 meter off the ground, off the surface of Earth, right? And I drop it and I want to know, how fast is it moving when it hits the ground, say. All right, so I'm going to start and I'm going to look at Amber's point of view. Right, so Amber does what many of us have probably done and says, okay, I'm going to define my origin as 0 in the y direction as being the surface of Earth. We've done that a lot of time in kinematics. We've said we have the freedom to choose wherever our 0 is, so why can't she do that, right? Now, if I want to analyze this problem, again, we're essentially bookkeeping where energies are. And if I look at this situation, well, I have an object at some height, so it's got some gravitational potential energy. I need to worry about kinetic energy. I don't have to worry about any dissipative forces or thermal energies because we're not worrying about air resistance and there's no friction. And there's no external forces. There's gravity, but I'm considering gravitational potential energy. So I've already considered that force. So all I've got is gravitational potential energy and kinetic energy. And I can essentially say, well, I have my initials and I have my final. And because there's no work being done or thermal energy or anything like that, these are going to be the same. So I have initial gravitational potential energy plus initial kinetic energy has to be equal to my final gravitational potential energy plus my final kinetic energy, right? And if I look from Amber's point of view at this problem, well, my gravitational potential energy at the start is the mass of the rock times g times y initial, and my kinetic energy is 1/2 mv initial squared, and that's going to be equal to the same thing, but the final values, 1/2 mv final squared. And now I can think of, well, in her coordinate system, my initial velocity is 0. It started from rest, so that whole term's going to 0. And my initial height is just 1 meter, so this ends up being 1 kilogram times 9.8 meters per second squared times 1 meter. And this is going to equal 1/2 mv final squared. And this is just 9.8 joules, right? Is equal to 1/2 mv final squared. So, we could plug in 1 here and take the square root in that and figure out v final. But essentially, she's figured out v final. Now, if I do the same thing over here from Bill's coordinate system, now Bill says, well, I'm going to make my origin where I start. I'm going to start at everything being 0. And again, just like in kinematics, we have the freedom to choose that 0. So why can't I do that? And again, he's going to follow the same sort of thing. Just bookkeep those energies from the initial to the final thing. We've got mg y initial plus 1/2 m v initial squared is going to be equal to mg y final plus 1/2 m v final squared. And again, all we're doing here is keeping track of the energies in our system, that bookkeeping, right? We know we've got kinetic energy, we've got gravitational potential energy because they were at some height above Earth. We don't have to worry about any changes in thermal energy because there's no dissipative force, there's no air resistance or friction here. There's no external forces, so the work that is going to be 0 as well. So all we're doing is keeping track of the 2 types of energies that are relevant in this problem, gravitational and kinetic. But anyway, back to Bill's point of view. He started at 0, so he has 0 gravitational potential energy and 0 initial kinetic energy. So he has 0 joules at the start. So that's a big kind of curiosity. He says at the start of this whole process, when that rock's up at 1 meter above the ground, that there's no energy in the system. There's no kinetic energy because it's not moving. There's no gravitational potential energy. Whereas Amber says there's 9.8 joules of energy. And this may seem like a contradiction, right? But if we continue Bill's analysis, what we find is at the final position, when the rock's down here at -1 meter, we have mg y final plus 1/2 mv final squared. We can bring this over and do some algebra. Then we have -mg y final is equal to 1/2 mv final squared. Y final's -1 meter, so this ends up being -1 kilogram times 9.8 meters per second squared times -1 meter is equal to 1/2 mv final squared. And these 2 minus signs cancel, so we end up with the same 9.8 joules is equal to 1/2 mv final squared. And what we calculate for our final velocities or our final kinetic energies are going to be the exact same no matter which coordinate system we use. And this is, so it's interesting, it's kind of nice that there actually isn't a physical conflict between defining these potential energies. And the reason is we're free to choose where our 0 of potential energy is in these systems, just like we were free to choose our origin in kinematic problems and put the coordinate system anywhere we want. We can do the same thing with potential energy. And the reason this comes down for is, if you remember back a few slides ago, we didn't define U as equal to mg y. This was at the end where we finally said, okay, let's simplify things. What we actually defined was the change in potential energy was negative the work done by whatever interaction we're looking at. So the change in potential energy is what's important here, not the individual values at any given point, right? So we could have made our origin, 100 feet off the ground, and it wouldn't have made a difference because when we did the change, both sides, Bill and Amber's coordinate system would both have that same 100. And when you did the difference between the start and end points, those would just cancel out. But the point is, um, well, there's a few points here. One is the zero of the potential energy is arbitrary. You can pick it anywhere you want and it won't change any physical result of the system because what we're really looking at or interested in is changes in potential energy, not the absolute value or not the value of potential energy at any given point. The other main thing that hopefully we can kind of get from this example is this sort of idea that all we're doing is bookkeeping what our energies are and keeping track of where they are in some process, right? If we looked at this problem, the first thing we had to do is just sort of think about the energies that are involved in the problem. Obviously, there's always going to be kinetic energy. If you have anything that's moving, we have to consider kinetic energy. Yeah, then you can think about what potential energies might be changing. And in here, we have a change in height, so we know there's going to be gravitational energy that we have to worry about. The thermal energy that we've discussed, well, that only changes if we have some dissipative force, and we don't, so we don't have to worry about that. And then, are there any forces that would cause some external work to be done? And we didn't have that. So after we went through all of that and sort of thought about the problem, all we had to do is look at the initial and the final points and consider what the energies were at those two, at the start and at the end. And then after that, it was, maybe a line or two of algebra before we got to what our final answer was. Anyway, again, practice is going to get us comfortable with this. We'll do some examples in our synchronous sessions. You can ask questions there. You can also email me, and I will we'll start to figure this out and get really comfortable with it.